All right, let's start going over it. First things first. Obviously, all of you guys are here, but this is for if you missed in the last month, or those of y'all at home watching this video. I'm sure you are. What's up, Caleb? Huh?
It's not.
Never mind. Listen, I need y'all to hear me clearly on this. Y'all taking an AP level class. It's a college level class. You miss a day of college. Half the time you're once you get past like 3 days or 5 days, depending on what class is, your grade's just going to stop dropping for missing a day of class. And then you are still personally responsible for making up what you missed. There's not going to be videos online for you to watch. In my class, there are. You need to take advantage of those if you miss a day of class. The AP exam is a month away. And we have got to make sure we know these inference procedures. Like, point blank period. Inferential statistics in some form or fashion accounts for the majority of the test, or at least a good chunk. I'd have to go and look. But you've got to know these foundations from proportion, so we're going to go over this free response question. Y'all got 2 days before your test to master as much of this as possible. What was frustrating for me is when I gave one assignment that honestly should have been the simplest assignment of go watch at least 3 videos from AP Classroom, and I think 3 out of 9 students did that. That's problematic. Why are you looking at me like that right now?
3 people?
Yeah, right. Yes, that is my problem. Progress checks, when only 5 out of 9 students are doing progress checks consistently, that's a problem. Guys, I want you to be successful. I want to support you in being successful. I'm going to do it, bust my butt to help you get there, but some of us got to pick it up. We got to pick it up. All right, I don't know why I disconnected, but here we go. What did I just press? What? What did I press? That's what I did. Any day now, please. There we go. No, click that. Duplicate. Alright. Here we go. Finally. We're going to go over this AP free response question. Then we're going to look at the DYU questions from the one student who asked DYU questions. And then we're going to look at a couple of progress check questions based on what the majority or more people missed than got right. Okay, so here's the AP free response. First things first, if you are given an inference question, what do you got to go through?
4C method.
The 4C method of inference, right? In the textbook it talks about state, plan, do, conclude. I don't care what you call it. The 4C method for me makes the most sense. I didn't always love state, plan, do, conclude. So what's that first C? Choose, right? So we got to choose the correct inference procedure. What do we see there that tells us which inference procedure to use? Looking at statistical difference, so that tells us it's a test or interval. Test, right? Technically you could assess it with an interval, but it's a test. What else do we see there?
There's 2 different samples.
There's 2 different samples, 2 different populations, right? So that comes out to be a 2-sample test for a difference in proportions. Something to that effect, 2 prop Z test. You can call it any of those things. What other things should we have inside of our choose? We need to define our parameters. What else do we need? The hypotheses.
What P1 and P2.
So that's defining those parameters and
significance level.
the significance level. Those are the things I'm always going to put in there. Let's check see what we got here. Notice they define the parameters first, and then out of those parameters they talk about the null and the alternative hypothesis. I will say this. I think we've been writing it as the P aspirin minus P placebo, and then talk about that and defining it. I actually do prefer this method. It makes more sense to do P aspirin represents the population proportion of adults similar to those in the study who would have developed colon cancer within the 6 years if they had taken a low dose of aspirin each year, which that's a lot, but that is directly from the language of the problem. Couple of details I need y'all to pay attention to and then P placebo for the placebo there. We got a null hypothesis. The difference is equal to 0. Remember, null hypothesis is always a statement of equality. Alternative is always inequality, right? And so here's the big thing I need y'all to pay attention to right here. When I gave you these rubrics, if you want to look at the rubrics, but that word right there, or that phrase right there, why am I highlighting that?
Because it means it's defining the whole population of who would.
And so it's not just the people in the studies, because notice it is similar to those in the study, but you have to be careful when you say who would do this, because then we're saying those outside of the study. If you make it about those within the study, we don't need to do an inference procedure with them because we know about them. The whole point is about the population. They talk about them in the textbook. Hold on to the idea and pay attention to that. So, what's the rubric say? Essentially correct if you identify the correct parameters and both hypotheses are labeled and you state the correct relationship between the parameters. Now, one thing I do want to point out here, you usually will not see me do P1 and P2 because there's no real meaning behind P1 and P2. I would do something like this. And on this AP exam, they're saying that that is sufficient without you having to define the parameters. I would never say that's sufficient. Write out your parameters. It's going to be good to have that context right now because you're going to have to do it again later. But yeah, sometimes they do that. They're not consistent all the time, but defining the parameters will always get you to that evidence. All right, questions about step 1? Going once, going twice. Okay, so after choose, what do we have to do?
Sure.
Check our conditions. Which conditions do we have to check this time around?
10% and large font.
So close.
Assignment.
So we need a random assignment. And what else?
What's the other one? Yeah.
Huh?
I thought we were doing
Random sample.
Oh.
Notice this was not random sampling. In fact, if you did random sampling, you will lose some evidence of understanding.
What
But
if you wrote random sampling, then like wrote in quotations when they said randomly assigned?
be careful on that with the AP exam. You would not get credit for that. You need to pay attention that it's random assignment because what type of study is this?
Experiment.
An experiment, right? So we have to have random assignment. But what other conditions did we have?
10%. I don't know,
We did not have 10% this time.
because it's
Because it's what?
an experiment.
An experiment. Remember, 10% is sampling without replacement. We didn't sample. We took volunteers. We assigned those volunteers to studies, or to treatments, but we need to recognize that 10% is when sampling without replacement. This rubric did not take off for that, but I have seen rubrics take off if you don't recognize that we didn't need 10% here. Okay, so 10% conditions only with sampling without replacement, specifically. Alright, so notice here's where you actually had, I don't know why they put it into step 2, but you needed to, because it's by formula. You had to identify a correct test procedure. Sometimes they accept it by formula, but I would argue writing out the name of it will help you get to the formula, so I always put the name in the choose, and then the formula within the calculate, and we have to check the appropriate conditions. Alright, so appropriate procedure is a 2-sample z-test for comparing proportions, or difference in proportions. Randomized experiment. The first condition is that the volunteers were randomly assigned to one treatment group or the other. Alright, we are told they were randomly assigned. Okay, so we'd have to say that. Not that full paragraph, essentially, or 2 sentences, but yeah. Now, I will say this. This is not the condition they would check anymore. This was in 2015, I think, is what this test was. Does that sound right?
Mm-hmm.
So it says. What's wrong with this condition that they're checking?
It just says counts are large enough, it doesn't say.
It's not essential in the theorem, it is, but it is large enough counts. I mean, we need the large count condition, but this is not how we would do the large count condition today.
You do the PC thing.
Remember, when it's a test, we are assuming that P1 is equal to P2, or P aspirin equals P placebo. So we actually need that combined sample proportion. So in 2015, they did not require that. Since the updated course and exam description, they will require that you do the combined sample proportion times N for aspirin, the complement times the sample size for aspirin, and the same for the placebo. So please keep that in mind. I'm emphasizing that for a very clear reason. You need to pay attention to that detail. All right, and it does say large enough. You need to actually compare it directly for more modern exams. Yes, ma'am?
You know when they changed that?
When the course exam description was updated, the year before COVID hit, so in 2019.
Oh,
And I will say this, there were rubrics even before 2019 that did require that, but they made it official on that course and exam description. All right, so we had to identify the correct test procedure by name or by formula. Note the use of random assignment satisfies the randomness condition. Notice right here, for the randomness component, it is minimally acceptable to say random assignment, check, but not acceptable to say random check or SRS check. Right? You had to recognize that it was a random sample, so you need to get into practice of saying random assignment. You have to say random assignment or random sample. It's got to be one of those two things.
So how do you?
Go ahead.
Oh, I thought she.
What?
Oh, I just have, remember we're done with this, can I just back up, because my contact is like,
If you gotta go take care of your contact, it's not gonna help you to sit here.
I can see you out this eye.
Okay. What you got?
So how would you like say that it's random assignment? Like how do you prove it? Like I just put it
Oh, I would literally have just circled it and say, what they're just saying is you can't just say random assignment check. You would need to say random assignment was stated in the STEM or whatever.
Okay.
Like it says random assignment up there, doesn't it? Or they were randomly assigned, right? So I would circle that and put random assignment and then maybe draw an arrow to there or just say, hey, it is stated the people were randomly assigned. Right here, you could just say, we are told the volunteers were randomly assigned. It's an extra little bit,
So-
but that's all I would do.
Would quoting the question be acceptable?
Sure, yeah. You just gotta make sure you say random assignment, not random sample, okay? And so yeah, you would lose some evidence here. So if the response implies the study used a random sample, randomness component is not satisfied because it was a volunteer sample, I believe, okay? Right here, checks for approximate normality of the test statistic by citing that all 4 counts are larger than some standard criterion as 5 or 10. You may have seen that on the progress checks. They do have it sometimes where it's 5. We always check 10, and it will always be at least 10. We do use 5 in a different setting that we'll look at when we get to chi-squared distributions. Yeah, they say normality check may use the expected counts. That's this combined sample proportion, which is what they want now. When can you use the observed counts? Not in a test, but in a interval, right? Because remember, in a confidence interval, we're not assuming those proportions are equal, okay? All right. So here's all the calculations. Notice how they use the combined sample proportion right here. But remember, do we have to make our life hard and do all those calculations by hand, Nate?
No.
No, that's a hard pass, right? Okay. Remember, set up your general formula, your specific formula, substitute stuff in, but what am I using really to do all these calculations? Calculator, right? Make sure you get your z-score, make sure you get your probability, which would be that from the calculator, okay? So make sure you're using a calculator. I'll run through the calculator for those of us who need it in a second. But big things that we want to notice off of this immediately, when I see this value, what does that make me think about?
It's less than the significance level.
It's less than your significance level of 0.05. Did they tell you a significance level on this one?
Yeah.
Okay. If they don't, what are you going to assume alpha is? 0.05, right? Okay. One thing I will say, they don't require it on this one. If I were you, I would draw out my normal distribution every single time. Just a quick sketch. It makes it easy to justify your answer. Serena, just glancing at yours, it looks like you went the other way with your difference. So you did placebo minus aspirin. Is that going to be completely okay? 100%, right? Like the order doesn't matter. It'll give you the same evidence. You would just be looking at greater than a positive 1.75 for your z-score.
Yeah.
Okay, totally acceptable. Notice right here it says the response correctly calculates both the test statistic and p-value that is consistent with the stated alternative hypothesis, right? So as long as you have it set up correctly and you follow that, then you're going to be good to go. Make sure you pay attention to those things. Notice the p-value is considered correct if it is consistent with the alternative and the calculated test statistic, even if those are incorrect, right? So again, if you do things incorrectly, but you follow the order of what it's supposed to be, you're gonna be good to go. Conclusion, the p-value is less than the given significance level, we reject the null. The data provides convincing statistical evidence that the proportion of all adults, similar to the volunteers who had developed colon cancer, if they had taken a level blah, 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 blah. This is just taking the context from earlier. So, conclusion about the null hypothesis, evidence for or not for the alternative hypothesis, and context. That's it. Now, one thing I want to point out is this, a couple of details. You need to write out from the beginning, choose, check, calculate, conclude. Do everything you can within each of those sections. Because even if you miss some part of one of those things, if you got stuff written down, you can at least earn a P. And what I would also point out is, on the step 2 here, can you get the majority of this straight from the calculator? Straight up, it literally just says here, correctly calculates both the test statistic and p-value. Normally you're going to have some work with that. That's where the formula sheet is great. But all you had to have was your z-score, the standardized test statistic, and the p-value. The calculator can spit that out for you. Even if you get lost on the calculate portion, if you make up a p-value, can you make some conclusion here? So if you write down a random p-value, and you then compare p to alpha here, and write your conclusion in context, which that doesn't require you to know any of the statistics, except to know that if p is less than alpha, you reject the null because there's convincing evidence for the alternative, and if p is greater than alpha, we fail to reject the null because there's not enough evidence for the alternative. If you can do that, you can always earn an E on the conclude. So I don't care what happens, earlier on, everyone should be able to get the conclusion portion because we are basing it, we're at least making up a p-value. Notice it even says the conclusion must be related to the alternative hypothesis. If the p-value is incorrect, then step 4 is scored as E if the response includes proper linkage and a conclusion in context consistent with the p-value. So pay attention to those details. Yeah, that's all I wanted to say there. We're going to look at this in a second. Calculator though, reminder, if you take the time to identify that we have a 2 proportion Z test, you go to your statistics test, 2 proportion Z test, and it does the work for us. What was the number of successes in that problem for the aspirin?
Aspirin is
50?
15.
15, thank you, that makes way more sense. Sample size? 500. Placebo? 26. And 500. And less than, right? Aspirin is less than placebo?
Yeah.
Notice it does the work for us. There's my p-value. There's even my combined sample, sample proportion right there. There's my z-score. Draw out your normal distribution. The last thing I want to remind you is when we talk about our hypothesis testing, you've got to make it who would do this thing because it's about the entire population, not the sample, and you have got to make sure that you look at cause and effect when it's an experiment. That's what I was looking for in those Ferrer models. All right. Any final questions before we get to the going over some details from demonstrate your understanding? All right, so now you got to go. All right, so I'm going to look at a couple of the true false quickly, and then Ms. Kowalski, you're up for the stuff after I go over the DYU. Yes, ma'am. You need a physical copy of the DYU. Ms. Kowalski, do you remember where we put the physical copies, or where you put the physical copies of the DYU last week?
No, they're probably on the table. I didn't see any extra much.
I can reprint it if I need to. Here you go.
So what do you find convincing evidence for the alternate?
Mm-hmm.
Okay, so now for the null.
Mm-hmm. Well, that's one of the sheets, not. Okay, I'll put it. Yeah, so that's why I put that question in there. We never prove anything. Don't ever forget that. We never prove in statistics, right? That's the wrong one. Never prove, find evidence for stuff. There we go. Oh, no. Nope. Yep, that's it. Lana, can you come grab it? So we never collect evidence for, we never prove anything, and we never collect evidence for a null. It's just, we collect evidence either for or for the alternative, and we either have enough or we don't have enough. Make sense? So keep that in mind. We either have enough evidence for the alternative or we don't have enough evidence for the alternative. So number 5, this one, even if I had y'all do true false, I wouldn't have had you worry about this one, but it is important to note. A lot of people would think the observed significance level is our alpha. Yes, you want a copy as well? Huh?
I haven't done this yet. I thought you did.
Well, you're taking the test on Wednesday, so I need you to learn from this, and then how did they send you the solutions?
I know, but that's why I'm asking, like.
No, I need you to learn from this, take the test on Wednesday, and I'll replace your BYU grade with this.
Okay.
Does that work? Okay. A lot of times people would think that observed significance level is alpha, but alpha is the significance level. If it is observed, it's a p-value. Okay? And so we compare our observed significance level to the significance level. So p-value versus alpha, beta, probability of that type 2 error. So I made a note here. Peter realized there was actually a second error with number 6. 99% would have 2.576 for the critical value. And I missed that detail. So that's something to hold on to and pay attention to as well. And then large counts condition for one sample, n times p, not n times 1 minus p. And it's not necessary for the standard deviation. What's necessary for standard deviation formula of the sample distribution? 10%. If you're sampling without replacement, the 10% condition is for the standard deviation of the sampling distribution. That's my large counts right there. All right. So this number 9 right here, a one sample z-test for a population proportion was conducted. Assuming the conditions for inference were met, which combination of sample proportion and sample size would result in the smallest p-value of the test? So first things first, I think we need to recognize that the higher the sample size yields a smaller what? Smaller spread, right? So in general, we want a high sample size, right? Sound fair? Okay. However, if we picked A and my null hypothesis is that p equals 0.35 and I collect a test statistic of 0.35, what's my p-value going to be?
Oh, yeah.
It's a two-tail. My p-value is 1. I'm not rejecting jack with that. Okay? I need y'all to recognize that if my p is, if they're the same, I'm not going to reject a single thing. What's going to give me a smaller p-value? If I have 0.25, that's way over here. Even a 0.4 would be close to the 0.35. So the thing to recognize is the further our sample proportion is from the null hypothesis, the smaller the p-value. Higher sample sizes result in smaller or less spread. A further sample proportion from the null hypothesis, the smaller the p-value. Okay? So, small p-values when your statistic is further from the null hypothesis. All right, number 10, someone specifically asked for this one. So, so it says, is there convincing statistical evidence of a difference between two population proportions at that significance level? I mean, first off, I would run the hypothesis test, right? If I run the hypothesis test, this is the p-value that I get. Just initially, do I have statistically significant evidence?
It's about 0.05.
So do I have statistically significant evidence?
Yeah.
So remember, you have statistically significant evidence when your p-value is less than alpha. Because that's how, so if p is less than alpha, it is so unlikely by chance alone. Because remember, we assume the null to be true, that we reject the null. Okay, so if the p-value is small, we reject the null hypothesis. So that's why it was D. Okay. Was there one of these other ones that was really distracting to us? Are we all realizing now why that's it?
Yeah.
Okay. Number 11, this was one of the ones, again, I told you not to do. Pay attention to this though and be careful. So Dan selected a random sample of 100 students, and 58 wanted to extend the school year into the summer, 42 wanted to go to school on Saturdays in the spring. And so he incorrectly performed a large sample test of the difference in two proportions. I mean, he has two proportions, right? So why is that incorrect? How many samples did he have? He only had one sample. He took one sample and split into two proportions, but that was only one sample in the first place. You cannot do an inference, a difference in proportions unless it's two different populations. In fact, there's a detail right here that I made a note of myself. When we say random condition with two proportions, something I need to say is it needs to be two random and independent populations with sampling. With an experiment, that's not the case because you randomly assign. But with a two proportion interval or hypothesis test, that we're trying to make an inference out of population, it has to be random and independent samples. Random and independent. And again, that was only one sample. All right, this was the last question. A lot of stuff there. You can go read it on your own, but also it's just following the hypothesis testing. Is very similar to what you actually just did. Choose, check, calculate, conclude. I'm mostly going to talk about the last couple things. Do notice I did my large counts using the combined sample proportion, and did I calculate that by hand? Heck to the gnaw. I used the calculator. A detail I want to remind you is this. Once I get done with my choose and I know which test I'm going to do, I'm going to run it in the calculator. I didn't say I'm going to do check and then calculate. I'm going to run my test in my calculator at this point, because the calculator is going to spit this out so that I can check my condition for approximate normality. Do notice I just calculated each of these values and said all greater than or equal to 10, so sampling distribution approximately normal. And so I didn't do the general formula, but I wrote out my specific formula, substituted my values in, got my z-score, and do you think I actually did all that work right there in the calculator?
No.
Heck no, I used the calculator, I used the two proportion z-test. Got my test statistic, marked it on my normal distribution, got my p-value, and that's way less than 0.05. Two things based on what I just noted. Please notice, I said the sample was randomly selected. The two samples were randomly and independently collected. Which, did the language say that? No, I'm going to update it for future assessments, but that's something you need to be aware of right there. It's got to be two randomly and independently selected samples. Okay. And so I think there was a couple of questions here. So I want to talk about B. First off, it says, based on your conclusion from part A, which type of error could have been made? So right here, we what? Rejected the null. So the only type of error we could make is we reject the null, but the null is true. That's a type 1. This could have been a type 1 error where we think there is a difference in the true proportions, right? We reject the null hypothesis, but there actually was no difference. Right? So that's a type 1 error. Okay? Shereen, does that answer your question you had with that? What was your question?
I don't even know.
Okay.
Did you say like D?
Hmm?
Did you say D?
I thought didn't you say B, C, and D? Okay. Does that make sense? I thought isn't that what you got on that, roughly?
I mean, yeah, I just got kind of off the language,
Hmm. What was the language, what did you say?
like assumed.
Say it one more, read out what you said so I can hear it.
We could have made a type 1 error and assumed the null hypothesis is false when it is actually true because we got it.
Oh, yes, learn from this. We're not assuming the null hypothesis is false. We collected enough evidence for the alternative. And so be careful, we don't assume anything in statistics, we don't prove anything, we base it all on evidence. So we collected enough evidence for the alternative. That's what that is there. Okay? Alright, part C, I just wrote out the formula and then used the calculator to get the confidence interval there. With 95% confidence, the true difference in proportion of males and females skipping in the last week is captured by this interval.
I'm just gonna put it here.
Is that my phone? Oh, that's my watch. Oh. Alright. Ooh, we gotta get going. So please notice, these are all of my what type of values? Plausible. You know what's not plausible then? Starts with a Z. 0. Meaning we think there has to be a what between those two proportions? A difference, right? Since that value of 0 is not captured by the interval, that is not a plausible value. Remember, a confidence interval is plausible values for our parameters, indicating there is, or I should say there's conclusive evidence for a difference in those true proportions, which isn't that the same thing that we said in part A? The p-value is way less than alpha, so there is convincing evidence for the alternative. Alright, we gotta get going. Ms. Kowalski, you ready to run through these, let's say 10 to 15 minutes so we can start on the next unit. So this will be our last little bit where you can ask questions, yes, Anaya?
Can you please come over here and look at my eye? Like, dude, I had to take out my contacts, but it's like
What?
really hurt.
I see
There's
those
a little red
packets.
on the outside, but not much.
Yeah, get ready. I
Freaking
can't.
Do you need to go see the nurse?
Okay.
Run your
Maybe.
progress check B.
Right, guys.
I think, did we go over progress check B already?
I thought we did.
No, we just
I mean-
did it. You skipped to C.
That was D.
We skipped D, and I think it was C,
No, you skipped D.
something like that.
Huh?
You skipped
No, I
D.
skipped C.
Yeah, he skipped
No,
C.
we didn't do this one yet.
Okay. One sample z-test for population proportion P will be conducted. Which of the following conditions checks that the sampling distribution of the sample portion is approximately normal? What do we think? 2?
Yeah.
We're good. Oh, does it not give us, did you not do?
I didn't put the answer choices in there, that's my bad. Is that the 7th?
Yes. Oh, why 2? Large counts, okay. What else?
Check the normality, or approximate normality.
Oh, there's- The first one checks for,
Independence.
Well, we're just checking for normal.
Right, we're just checking for normality. So are there any other ones that check for normality? No. Right?
Yeah.
Right.
So yeah, just be careful with the language. A lot of people would be very tempted to pick 1 and 3 just because it's a confidence interval, right? Yeah, Ms. Kowalski, or Z-test. But read the details. The devil's in the details. Attending to the details is the most important part.
Why is it not on?
Because this one is the only one that checks for normality. You do all 3, but the only one that checks for normality is large counts.
Okay. Okay. Thank you.
A newspaper article claims that 92% of teens use social media. To investigate the claim, a polling organization selected a random sample of 100 teens, and 96 teens in the sample indicated that they use social media. That was bothering me. Given the data, why is it not appropriate to use a one sample z-test for a proportion to test the newspaper's claim? All right. So our options are the random sample condition is not met. No, right? Right, so that's gone. The sample is more than 10% of the population. Is 100 more than 10% of all the teens?
No.
No. Right? We can get off of that one. The observed number of teens in the sample who do not use social media is less than 10.
This is observed.
What?
It says observed.
Like,
Did I not say that?
No, that's what he's saying is wrong.
Oh. Okay.
I don't know.
Right, because 90, what is it, 96?
Well, that is the observed. The problem is, can you click the thing real quick?
Oh, I didn't know if you wanted to show that yet.
Yeah. C and, yeah, I mean, we already got to this point. C
Okay.
and E were the most common distractors, leaving us with which answer?
the wrong one?
What answer do we have left and C and E were wrong?
D.
D! The expected number of teens in the sample who do not use social media is less. Oh, I read this one wrong. There is no observed. Hold on, now I'm having a stroke.
So,
Yeah, no.
yeah, so remember, this is a hypothesis test. So we need large counts, right? And with a confidence interval, we do n times p, for a confidence interval, n times p hat. That's for a confidence interval. That's the observed. But in a hypothesis test, we have an assumed p, so n times p, as Peter said, sub-zero. So we use expected number with a hypothesis test.
So observed is sample, expected is population.
Test. Hypothesis test. Use observed counts with a confidence interval. Use expected counts with a hypothesis test. The whole idea is that we assume the null hypothesis is true. That's a very small detail, but it's important to recognize.
Okay.
Oh, sorry, go back really quickly. Sorry, I just thought it was on test taking details. I need y'all to notice, you see how C and D are almost identical? That tells me right away it's probably C or D. Jaden nods his head yes. If you have not picked that up on standardized testing yet, they try to hide the correct answer with two almost identical answers, and so, or three, and so that's where you need to dive into the details and be like, ooh, is it observed or is it expected? What's my large counts formula again? And so that's what tells you where to go. It's a small detail, but it's really, really important.
Alright, Molly works for a meat producer and she needs to determine whether the containers of ground beef have the correct fat content. She obtains a random sample of 120 containers of ground beef and finds that 84% have the correct fat content. Molly then conducts a hypothesis test. H naught is P equals 0.8 versus the alternate is P does not equal 0.8 and calculates a test statistic of 1.10 with a p-value of 0.273. Which of the following best represents the meaning of the p-value? Alright,
Really quick, we can go back, but even before we look at answer choices. Hint number 2 for standardized test, you should know what a p-value is. Think through how you would interpret the p-value first, and then look at your answer choices. Don't look at the answer choices first. They're designed to hide things and make things harder to find. Okay?
so how would we interpret the p-value?
Assuming the population, wait, assuming I know that the population, the population proportion is 0.8. I don't say all that.
The probability of getting a value
Yeah.
outside of 0.04 or whatever.
0.84?
Or within. Or outside.
Is it within or
Which
outside?
one?
0.04 of 0.80.
Is that because you looked at answer choices when I told you not to?
Are you just
I'm so confused. I don't know.
Okay,
My head hurts.
okay. We're on the right track. We're on the right track. We're tired. Okay. If the population proportion is 0.84, the probability of observing a sample proportion of 0.8 is 0.273.
Can I just show this real quick?
Yeah.
So even before I look at this, because if you're, especially if you look at this and you get confused, you should know what's the center of this distribution. 0.8. What's our test statistic, or what's our statistic? Not standardized, just test statistic.
0.84.
0.84. And I know with that way hypothesis testing works, it's that or more extreme. But there's one other detail we gotta pay attention to.
Other way.
It's gotta be two-tail, right? Not equal to. That might make things a lot easier. Do not forget that p-values are based on the areas of those tails. Listen to those answers.
Jaden, is it within
No.
0.4?
I meant
Is
like,
it not
I meant-
equal
well,
to?
I meant outside.
Remember when it's
of
greater than, it's just
0.04
above, when it's less than,
of
it's just below,
0.8.
not equal to.
Okay, well,
both.
it's
So
not
basically
within,
what
I can
that
tell you that.
statistic was,
Yes, I'm
and
saying.
Not within.
mirroring on the other side.
Do we think it's that first one I just read?
No.
No.
And it's not B or E, because those are, wait, no, we're
It's
not
not
read
B.
it.
It's E.
Why is it read it?
It has to be easy because it's between the interval that we
Sorry.
have, the 0.8.
Yes. Because it's saying at least 0.84, so 0.84 or greater, or at most 0.76, so 0.76 or less than. So yeah. Most common was C and D. So not, this would be, I don't want to say this wrong, but this would be a confidence interval, no?
Kind of, like,
Like, the
yeah,
setup.
we think ish,
Opposite.
yeah,
Wrong.
yeah. Is it a complement of what we should be looking at?
Yeah.
Okay.
And then D, that's just not, we didn't recognize here that it was two-tailed. We chose D.
Yeah, so remember, if it is two-tailed, you literally just mirror it to the other side of the mean.
Alright, if all other factors are held constant, which of the following results in a decrease in the probability of a type 2 error?
So this is from last Wednesday and Thursday, I think?
No, progress check C is the one we did this weekend.
Sorry, let me re-clarify.
What we talked about.
This is from the lessons last Wednesday and Thursday, if you need to go watch these
Shoot
videos.
myself.
That was unclear on my part.
Okay, should I draw the box? Or no?
This one was so weird.
I wouldn't draw the box. You said this one's so weird? Okay, what do you know is related to the probability of a type 2 error? Sample size?
The A, because that's the significance level.
Okay.
What'd you say?
Isn't the true parent murder is closer to value than null hypothesis is the type 1 error?
Oh, this, I guess we do,
This one was really.
it could help with A, I think, but, okay, you go ahead, never mind. You do what you want to do with this, and I can think about other things
Okay.
along with it.
It's not A, because that's type 1. And we're looking at type 2?
Mhm.
If the true parameter is close to the value of the null, what is a type 2 error?
False negative.
So you fail to reject when the alternative is true. If the true parameter is close to the value, are you going to, oh wait. That's gonna increase the probability of type 2 error,
Told
right?
you this was weird.
Look, so like, and this is what I was looking at earlier. If I have if this is the truth over here, is that gonna make it easy or hard to reject the null?
Easier since it's farther away.
Yeah, further away it is, the easier it is to reject the null, right?
Yeah.
You go for it.
Oh, that was bad. That was bad.
Don't worry, don't look at it, don't think about it. I would put them closer, that's basically what I got.
Yeah.
Would that be harder or easier to reject the null now? Harder, right?
What changed?
The distance.
They're overlapped.
So what was decreased?
The spread.
The spread is for a single distribution.
I don't know now.
How the hell overlap?
I'll crash out.
The distance?
The true parameter is now closer. So, that would make it easier to make a type 2 error. What did you say though a second ago? Wouldn't that decrease our power? That's what I should have said, and that's what I was thinking about. Remember guys, this is part of the applet we looked at last Thursday for sure. They get further away, the power of the test increases. How's power and probability of type 2 error related?
Oh, how's the chance?
They're complements.
They're complements, right? So if I decrease the power, what's it gonna have to do to beta? Increase. That's not what we want.
Yeah, makes sense.
Why does that make sense, Nate?
Because alpha is the chance of getting the type 1, right?
Okay, so how did, help us here.
Because if you lower alpha, that in turn lowers the probability you can get type 2, right?
But we want to lower the probability of type 2.
That, I got it wrong. So,
Guys, we're kind of getting going. Let's go.
It's not E,
Okay, but why is it not C?
because the significance level
Did
has
you-
to,
Did it have to increase?
No, dude, Serena was just talking, bro.
Say it again?
the significance level has to do with the A value, and if the, or not, the alpha level, sorry. And if the alpha, if the significant level is decreased, then so is the alpha level, and that'll in turn increase the probability of type 2 error.
Right.
did I say it wrong?
Yeah, you said
Yeah,
that.
you mixed up your words. Alright, and why is it not E?
Because we literally just said that we can decrease.
We
it.
literally just said we can do that. So now we're stuck between sample size is decreased and standard error is decreased.
I don't know those
Not
terms.
B.
Why not?
Because sample size would reduce. The sample size, like increasing sample size would reduce the spread.
Right, so now we're left with D.
I don't understand why it's not B.
If you increase your sample size, that makes it harder to make a type 2 error, correct?
Okay.
Because it gets skinnier.
So-
Like the two things get skinnier, so there's.
And also, like, remember, if we increase the sample size, those sampling distributions have less variability, so it makes the power of the test go up, right? And if the power of our test goes up, then the probability of a type 2 error goes, whoa, what did you just do?
I'm so sorry.
There you go. Oh yeah, if the sample size goes up, power goes up, which means if the sample size goes down, the power goes down, and the probability of type 2 error goes up.
Okay.
So, the other thing is, if the standard error is decreased, when does standard error decrease? When the sample size goes up. The standard error decreasing is kind of like saying the sample size goes up. It's not the only thing that affects the standard error, but it's the most common one.
Alright. A new drug to treat a certain condition is being tested. The null hypothesis of this test is that the drug is not effective. For the researchers, the more consequential error would be for the drug to be effective, but the test does not detect the effect. Which of the following should the researcher
Researchers
do to avoid the more consequential error? So is it a type 1 or a type 2 error? Type 2 error, right? Because if we're saying the null is that the drug is not effective, more consequential would be to, hold on, would be for the drug to be effective, so it would be fail to reject the null with alternate.
I was like, they tell us which one they think is more consequential.
Yeah,
We conclude the drug is effective,
but
but
the test does not
the
detect.
test
the
does
effect.
not detect that effect.
So we fail to
Fail to reject when the alternate is true.
Alright, so which of the following should the researchers do to avoid the more consequential error or the type 2 error? So, should I go? Yeah, alright. Increase the significance level, so increase alpha to increase the probability of a type 1 error.
I need a backpack.
Ooh.
Shirley.
Sanaya.
Also, I have a question. What is this?
Did you not give them those instructions?
I did.
Okay.
I forgot.
You're supposed to say which strategy is most efficient to find. Okay. No, avoid, so we want to decrease
Probability of type 2.
probability of a type 2.
And we already talked about that. How are type 1 and type 2 related?
As type 1 goes down, beta goes up.
So as alpha goes up, beta goes down.
Okay. So increase the significance level, which is our alpha, to increase the probability of a type 1 error. Yes, no, maybe so. I mean, yeah. Yeah, right? It was A. Cool. The most common response, is that what that is?
Distractors.
Distractors.
People said D a lot. I think D is what got everyone on this one.
Decrease.
Yeah.
To
So-
decrease, but that would be this.
Yeah, if you decrease alpha, that does decrease the probability of a type 1 error, but we want to decrease probability of a type 2 error. So we actually needed to increase the probability of type 1 error. They're inverses.
Okay. Which defining indicates that the use of a 2 stable Z interval for a difference in population proportions is appropriate. I don't know answer choices here. Yeah, no.
Yeah, I forgot to put that up there.
2 populations of interest exist, the variable of interest is categorical, and the intent is to estimate a difference in sample proportions.
This is weird.
This is weird.
What threw us off on this one?
I just didn't understand it.
It was to say categorical. That's what threw me off.
And that's what threw you off as well, Ms. Kowalski.
And I haven't associated categorical to like these tests or anything yet.
Yeah, so if you look at the top of your proficiency scales, I need to be more clear about this, and I think most of the assessments, Unit 6 has been inferences with categorical data and then proportions, because either you do a thing or you don't do a thing, that's what type of data. Categorical, guys, if we're doing proportions, it's categorical data. If you're doing proportions, a relative frequency, anything like that, it's categorical data.
Alright, and then, it's also 1, right, 2 populations of interest exist, Mr. Kenny just talked about that, you can't take 2,
Can't be one population.
yeah, but you can't take 2 proportions from one population
Right.
and try to find the difference of them. And then the intent is to estimate a difference in sample proportions.
Because it's
It's
sample.
supposed to be difference in population.
Yeah. So it was 1 and 2.
It's all about populations.
2 schools are investigating whether there is a difference in the proportion of students who attend the homecoming football game. Both schools have over 2,000 students. School A selected a simple random sample of 100 and found that 98 attended the homecoming football game. School B selected a random sample of 150 and found that 142 attended the homecoming football game. Let P hat C represent the combined sample proportion for the 2 schools. Let it A and it B represent their respective sample sizes. Have the conditions for statistical inference for testing a difference in population proportions have been met. There you have it then. So we know E is wrong. Alright. Now, me and Mr. Kenny were talking about this. So A, we do know they were both random samples, right? So that doesn't matter. B, our sample sizes are fine. They are less than 10%. So we're stuck between C and D. And like Mr. Cooney said earlier, that sounds about right because they're almost the exact same. But why is it not C?
Or greater than, yeah, or you put it on.
Right, this one is. This, me and Mr. Cooney talked about this. Well, like, just sometimes they put 5. Like,
Yeah, there is some debate about whether it should be 5 or 10. We will always use 10 personally, but you'll see 5 and 10 show up.
so, but we do know that 1 minus our combined proportion is not greater than or equal to 10, right? Because we have, go back to our numbers. 98 and,
And technically, you would have to go through all the work to do it, but like you can, A, B, and E are all out.
right?
C is definitely not the problem, it's the complement that would be the problem.
Alright, independent random samples of students were taken from 2 high schools, R and S, and the proportion of students who drive to school in each sample was recorded. The difference between the 2 sample proportions, R minus S, was 0.07. Under the assumption that all conditions for inference were met, a hypothesis test was conducted where the alternative hypothesis was the population proportion of students who drive to school for R was greater than that for S. The p-value of the test was 0.114. Which of the following was the correct interpretation of the p-value? So, what should we do before we look at the answer choices? Think about how we would interpret the p-value. Anybody want to do that?
It's the entire next unit. It's confidence intervals and hypothesis test.
Okay.
For means. Sorry.
It's okay, we didn't want to interpret. The probability of, so A, the probability of selecting a student from high school R who drives to school is 0.07, and the probability of selecting a student from high school S who drives to school is 0.114. No, right? Like that makes no sense based on what we've calculated and found. Because 0.114 is our what? Our p-value.
I would also point out, notice how B, C, D, and E all start out the same? Test taking strategy, that probably means A is out. Why are the other 4 the same? Because they're trying to hide the right answer.
Alright, if the proportion of all students who drive to school at R is greater than the proportion who drive to school at S, the probability of observing that difference is 0.114.
No.
Why? It's not the null.
Same thing for C.
We
Same.
assume the null is true, that the difference is what? 0. That
So, we're stuck on these last 2. And again, like Mr. Kinney said, these 2 are the exact same, but what is different about each of them?
The number is like.
They flip the p-value in our
Statistic.
statistic. So, which one's correct?
Wait.
Yeah, D.
The probability is 0.114.
Cool, cool, cool.
I think that's the last one. Alright, and I apparently
Just
forgot to
kidding.
put the
Doing one.
slides in for confidence intervals for means. I apologize, but we gotta get going. We got an AP exam. Now, good news is, this is not going to hurt us at all in preparing for our test on Wednesday. It's loaded. I promise it'll be there soon. Alrighty then. We have one later coming up that's all about chocolate chips, and we'll actually get to eat chocolate chip cookies. But we're not doing that right now. We got Oreos. So, fun fact, you can do all this. Notice we are no longer doing proportions. What are we dealing with now? Means. Because what type of data are we dealing with? Quantitative now. So, sorry for not making that clear earlier. When we dealt with proportions, that was all categorical data. Today, we're all about some quantitative data. So, another way to notice that is, remember when we looked at like the proportion of Skittles that you could correctly eat and guess the flavor or color of, the proportion of whatever with the peanut and plain M&Ms, right? So those are all categorical things. All right, we want you to construct and interpret. So we got this package. 3 Oreo cookies should weigh 34 grams. We have an average weight is 11.33 grams. Skeptical AP Stat student wants to find out if this is true, so she selected a random sample of 30 cookies. The mean weight of the sample is 11.19 grams with a standard deviation of 0.08. Construct and interpret 95% confidence interval. First things first, I gotta point this out. Why in the world, what numbers jump out at you as being an interesting choice? Any? Nah, the 11 one's not interesting to me. No, there's a number up here that was interesting to me. I'm like, why in the world did they pick that? Ms. Kolsky, you notice what I'm talking about? Which number was interesting in that design?
30 cookies, 34 grams.
No, not 34. The 30. Why the 30?
Ah.
Oh, that satisfies central limit theorems. I don't know anything about the population, but does it matter? No, that sampling distribution is approximately normal. Okay, so I need y'all to work through, honestly, 1, 2, 3, 4, 5, 6, and 7. You got 5 minutes. Y'all can do it. It's just the front page. Guys, you can do all this.
Well, I got to going to upload the video from today and realized that all the discussion about this got messed up somehow. So here you go. Hopefully this helps a few of you who need me to go a little bit slower anyways. All right. So how much does an Oreo actually weigh? We've got a claim that 3 Oreos should weigh 34 grams, which means a true average weight of this, right? Skeptical stats students wants to find out if this is true, so she selected a random sample of 30 cookies, and their mean weight was 11.19 grams with that standard deviation. Construct and interpret 95% confidence interval. So remember your point estimate. That's just your statistic, estimating the parameter. And so we need to recognize that this is a mean and that the statistic is X bar. We've got to start paying attention to whether we have means or proportions, aka quantitative data, means, or categorical data with proportions. So population, all Oreos, sample, my 30 Oreos. Remember, we're essentially given a hypothesis or an assumption that the average weight of Oreos is actually 11.33 grams, but we're not doing a hypothesis test because the question was a 95% confidence interval, but we're going to use that interval to assess the average weight of an Oreo cookie. So parameter is mean. We don't know it. The true mean weight of all Oreo cookies. And we have a statistic X bar of 11.19. Oof, forgot the grams earlier. All right, was the sample a random sample? Well, we were told that she collected a random sample of 30 cookies. Yes, stated in problem. Why is this important? Quite simply because we want to, so we can generalize to the population of all Oreos. What is the formula for calculating the standard deviation of the sampling distribution of X bar? Now, technically, and I should have noted this during class today, I let everyone use S sub X bar, but for the standard deviation of the sampling distribution is still sigma sub X bar, sigma divided by root n. Now, that is going to become an issue in a second, and I will point that out on the formula sheet. Let me find one and pull it up. And then actually remember to change my share. So here's a formula sheet. Don't forget, we're in inferential statistics. We are no longer proportions up here at the top. We're now down here at means. And we need to notice the parameters of the sampling distribution, right? Standard deviation of X bar. And then we have our standard error of the sample statistic over on the right. But that's not where we are yet. So sigma sub X bar is sigma divided by root n. Condition, remember, in order to use that formula, we have to satisfy the 10% condition. Is it safe to say that 30 is less than 10% of all Oreos? Heck yeah, it is. Not, I was gonna say, I'm pretty confident that I've eaten more than 300 Oreos in my life, and I can guarantee that. 100% can guarantee that. I don't know about within the last couple of years, but probably. In the formula for standard deviation of the sampling distribution of X bar, we don't actually know the value of sigma, so we'll have to use S. And so that is known as our standard error. S sub X bar is the standard error of the sampling distribution, S divided by root n. And again, it's a natural substitute. We're estimating sigma. And so we are using S to estimate sigma. And so 0.08 divided by square root of 30. I believe that's what someone said in class. Yep. So using a handy dandy calculator, that standard error comes out to be 0.0146. Would it be appropriate to use a normal distribution to model the sampling distribution of X bar? And so we talked about this in class. Naturally, we want to say yes, right? The sample size is sufficiently large. Right, sample size is 30 for the central limit theorem. But the answer is no. Because sigma is unknown.
Recording in progress.
So when finding the margin of error for a confidence interval for a proportion, we use Z star. For a mean, we'll use T star as the critical value. And again, the Y is what I said before. We'll probably look at it in class for at least a little bit, but essentially the capture rate won't be right when sigma is unknown and if you use Z, right? So we've got to use a T critical value in that context. And so the reality is, and this is what I said in class, it's very unlikely you're gonna not know mu, but you know sigma, so you can just use this as a general rule of thumb for means. So what is T star needed for this confidence interval? Use table B and the degrees of freedom equals n minus 1. So degrees of freedom is always n minus 1. 30 minus 1 is 29. And so I showed this in class. If you go to the formula sheet, you scroll down to your T distribution. There we go. So we got our degrees of freedom of 29 right here, which I guess you can't easily see that, but 29 and there we go. And 29 is all right there, 95% confidence interval at 2.045. I will show in a second how to get that from the calculator as well. So much like z-scores, to get that value, we need to recognize that we're still looking at an area of 0.95 here. So I can use, and that's on the center, so I can use an inverse, but it would have to be t now with either of those areas for either that left tail or the tail plus that 95%. And so there we go. So just so you can see that it still works, probability or statistics, either one. Distribution, notice there's an inverse t now. So an area of 0.975 with the degrees of freedom of 29, enter. 2.045, right? So either way, it'll work, but for sure it's one of the few times where I'm like, yep, that table is awesome. Go with the table. All right, margin of error. So don't forget margin of, when we talk about a confidence interval, right, it's always a point estimate plus or minus the margin of error, where my margin of error is my critical value. Notice we originally said critical value, not just z-score, because it can also be a t score from a t distribution times my standard error. So remember, standard error of sample means was that s divided by root n. T here is 2.045, and so my margin of error is 2.045 times, what was that value? 0.014606. You can also just write it this way. Calculate a 95% confidence interval, so 11.19 plus or minus. Oh, I actually never found the confidence or the margin of error. And so 0.0299. I get 11.16 comma, yeah, I'll go there. These are means, not proportions. So I'll go to 2 decimal places if that was unclear. And 11.22. All right, I'm going to come back to that in a second, but first I do want to show you that all of this still holds true, even if you just run with it on the calculator. I am jumping ahead because, well, we've got an AP exam to get ready for. So confidence intervals. Do notice I cannot use Z interval. I've got to use a T interval this time. Now you can either do data or statistics. I don't have raw data, I have statistics. The mean was 11.19. Standard deviation, notice how to use S sub X instead of sigma here, 0.08. Sample size was 30. Confidence level 95%. Notice it tells me my degrees of freedom. It tells me my margin of error. Man, those numbers look real familiar. Same exact lower and upper bound for the interval, right? So take advantage of that for sure. I hope I shared that screen. Yeah, I did. Sweet. Okay, just as before, with 95% confidence, the interval from 11.16 grams to 11.22 grams captures the true mean weight of an Oreo cookie. All right, so specific formula for the confidence interval. Well, I'm going to always start with the general formula found right here on the formula sheet. Too far. Statistic plus or minus critical value times standard error of that statistic. So statistic plus or minus critical value times standard error. And that gives me a statistic of X bar plus or minus. We know the critical value will be a t-score distribution with whatever degrees of freedom times the standard error. And so I do want to go back quickly to the formula sheet and remind you, no longer dealing with proportions, on to means, and there's my standard error formula. S sub X bar equals S divided by root N. And there's my formula. I don't need anything else. So according to Nabisco, the average weight of an Oreo cookie is 11.33 grams. Does our confidence interval provide convincing evidence that the average weight is different? The answer is yes. 11.33 grams is not a plausible true mean weight of the cookies, of Oreos, I should say. Since that is not captured by the interval.
Recording in progress.
Now, as you may have noticed, the quick notes or the constructing confidence interval for mean, not very different than proportions, but a couple of quick things I want to talk about. One, conditions. First one, gotta have random. Either a random sample if it's an observational study or assignment if it's an experiment. Make sure you pay attention to that detail as we saw in the free response question today in class. Next, after that, you got to satisfy the 10% condition, right? Once again, this is only if sampling without replacement. The sample size has to be less than 10% of the population size. And then finally, we need to pay attention to this. We need our sampling distribution to be approximately normal. Now, we've already known that if the population is approximately normal, then our sampling distribution is approximately normal. Check. If n, our sample size, is sufficiently large, then we can check. You got to at least reference the central limit theorem. But there are times when the population is not approximately normal. In fact, most of the time, populations are not approximately normal with means. And we usually don't know the population. That's why we're doing an inference procedure. If the sample size, but a lot of times the AP exam will say assume the population is approximately normal. But if n is sufficiently large, we can invoke the central limit theorem. But there's times when the sample size is not sufficiently large. And so this is something we'll see this unit. I'm going to go ahead and give it to you. If the sample does not show strong skewness or outliers, then safe to assume sampling distribution approximately normal. So the idea is that, hey, if we get a sample size of 9 and or a sample of 9 and data points and it's roughly symmetric, no heavy skewness, no outliers, then we believe the sampling distribution is approximately normal. And so you'll see that throughout this unit. So go ahead and hold on to that. Last thing, we use Z critical values when we're dealing with proportions, but with means, we don't have sigma. So we're going to use our T critical values anytime we're doing that. And then degrees of freedom is equal to the sample size minus 1. And you can either use the calculator with inverse normal, or sorry, not inverse normal, inverse T and area, just like we did with inverse normal. Or, and my recommendation is use the formula sheet with, well, use the T distribution table. Okay. That's all I got for today. Hopefully that helps some of you learn and grow and be better prepared. And I'm going to stop the video unless I remember something later.
Recording in progress.
I'm glad I only paused the video and didn't completely stop it because I did remember something important. You will notice if you look at a T distribution table, it does not have every degree of freedom possible. For instance, if I get down here and I have, say, degrees of freedom of 32, that's not on this table. So you can still use a calculator to find that value, but on the AP exam, it's more than okay to say, hey, I have degrees of freedom of 32. I'm going to use degrees of freedom of 30 and a 95% confidence interval. Notice you want to go to the lower degrees of freedom. Even if it was 38 for my degrees of freedom, I would want to go down to 30 because that's going to give me at least the capture rate that I want, right? A higher T distribution is going to widen that interval out just a hair more and guarantee me a capture rate that's at least 95%. If I go up to 40, it's not guaranteed at least 95%. And so that's something to pay attention to. So if you get one of those degrees of freedom that's beyond 30, that may be something you have to do. All right, now I'm done. See ya.